All right, hello everyone. I have the last video here for standard 5, focusing on normal distributions. And in this video, we're going to talk about percentiles, finding cutoff scores for given percentiles or what part of the distribution. So in this question here, it says that newborn babies have an average weight of 7.4 pounds, so this would be mu, and a standard deviation of 1.6 pounds. Letter A says, what is the cutoff weight for the heaviest 15% of babies? So let's draw that distribution. The heaviest 15% means that I want to find the cutoff weight that separates the top 15% from the rest of the distribution. So this is actually the z-table in reverse. Rather than finding the z-score and calculating the probability based on the z-table, now we're given the probability and we have to find the z-score that cuts off that part of the distribution from the remaining part. I do not know what z-score puts the top 15% cut off from the remaining part of the distribution. So let's see if we can use z-scores to determine this here. If I know that the top 15% is in the right tail, that means that the remaining 85% is in the left tail. What z-score corresponds to a probability of 85%? Well, since I'm above the mean, above 50%, I know it's a positive z-score. And let's get as close to 0.85 as we can. And I think I've done so right here. .85 is roughly 0.8508. So a z-score of 1.04 cuts off the top 15% in the right tail from the lower 85% in the left tail, 1.04. Okay. So I know that I need to be 1.04 standard deviations above the mean to find the cutoff weight. Well, the mean and standard deviation are 7.4 pounds and 1.6 pounds. So that cutoff weight is going to be our mean of 7.4 with 1.04 standard deviations added on. So 1.04 times 1.6. I know I need to be 1.04 standard deviations above the mean because that separates the 15% in the upper right tail, the heaviest 15% of babies, from the remaining 85% in the lower tail. A standard deviation is worth 1.6 pounds, so I take 1.04 times 1.6 pounds, and then add that on to our average baby weight of 7.4 pounds. So I'm 9.064 pounds. A baby in the 85th percentile, where only 15% of babies would weigh more, would weigh 9.064 pounds. Now in part B on the next page, we're going to find the cutoff weight for the lightest 40% of babies. So we'll begin again by drawing a picture. And I need to find the cutoff score where 40% of the distribution lies to the left. Now this question is the previous one because I wanted the top 15%. So I looked up 85% because remember your z-table is aligned to be giving you the probability for the left tail, the left side of the distribution. Well, I already want the left tail because it says that I want the lightest 40% for the cutoff weight of these babies. Once again, this is a percentile. It's in reverse. We're given the proportion of the distribution, 40%. And I have to figure out what z-score corresponds to that cutoff percentile. So let's do the best we can to find 0.4 on our z-table. Since 0.4 is less than a half, I know it's going to be a negative z-score. I know I'm less than the mean. So 0.4 is roughly right here. So that would be negative 0.29876, negative 0.25. So in order for a baby weight to cut off the bottom 40% to be in the 40th percentile, it needs to be 0.25 standard deviations below the mean. So how much is a standard deviation worth? It was 1.6 pounds. So negative 0.25 standard deviations, which is 1.6 pounds, below the mean, which was 7.4 pounds. To be in the 40th percentile, that means you're 0.25 standard deviations below the mean. A standard deviation is worth 1.6 pounds, and the average weight of babies is 7.4 pounds. So 7.4 minus 0.25 times 1.6 gives us a weight of 7 pounds. Which means that given a normal distribution, 40% of all babies would weigh less than 7 pounds. A baby that weighs 7 pounds is in the 40th percentile of all weights. For letter C, what are the cutoff weights for the middle 50%? Middle 50%. Cutoff weights, which means there's going to be 2. Because if I draw a picture, the middle 50% is defined by 2 values, a cutoff score to the left and a cutoff score to the right. Now, what part of the distribution is to the left of each of these 2 cutoff scores? In order for us to look those up on the z-table. Well, if 50% is in the middle, that means that there's 25% on either side. 50% is in the middle, so their other half is in the 2 tails. Each of the 2 tails has to contain 25%. So the cutoff score for this weight would be in the 25th percentile. The cutoff score for this weight would be in the 75th percentile because it's the 25% in the left tail and the 50% in the middle. So let's first look up the z-score that cuts off the bottom 25% from the rest of the distribution. 25%. I think the closest we can get would be about here. 0.2514 is closer to 0.25 than 0.2483, so we'll call this pretty good. So negative 0.6987, negative 0.67. To be in the 25th percentile means that you are 0.67 standard deviations below the mean. Now for the top cutoff, that's in the 75th percentile because it's going to put 50% in the middle and 25% in either tail. So let's get as close as we can to the 75th percentile. That would be above the mean. 0.6, 75%. 75% should be about here. 0.7486 is closer to 75% than is 0.7517. So this would be positive 0.7. Notice that these 2 z-scores are the same because the normal distribution is symmetric. 25% in the left tail should be symmetric with 25% in the right tail, which means that a z-score of negative 0.67 cuts off the bottom 25%, and a z-score of positive 0.67 would cut off the top 25%. So we need to find these cutoff weights using the z-scores. How many standard deviations below the mean for the bottom 25% and above the mean for the top 25% to put 50% in the middle. So we had 7.4 pounds minus 0.67 for our cutoff z-score times a standard deviation of 1.6. And that's 6.328. And then we had plus 0.67. $8.472. So the range of values would be 6.328 to 8.472. I know that to cut off the bottom 25%, I'm 0.67 standard deviations below the mean. A standard deviation is worth 1.6 pounds, and I subtract that from the average of 7.4 pounds. To cut off the top 25% and put 50% in the middle, that means I'm going to put 0.67 standard deviations above the mean. And by that same reasoning, I'll add on 0.67 times 1.6 to 7.4 to get that top cutoff weight. This gives me the knowledge that 50% of all baby weights are between 6.328 and 8.472 pounds, the middle 50% of all baby weights. We can use the z-table in reverse to take these percentiles and find the z-scores that cut off this part of the distribution. That's going to wrap up Standard 5. Thanks, guys.